Thank you. Good morning, everyone. Thank you for having me here today. I'm really excited today to tell you about a novel process that I've developed to fabricate highly oriented nanowires with some really cool applications. So let's get started. The motivation for my project begins with electronic memory. As some of you may know, we classify device performance based on these categories. Unfortunately, today's devices have strengths in some and weaknesses in others. This has given rise to the search for what's called a universal memory device, or one that can combine the strengths of all of these devices into one. And in this search, nanowire-based phase change memory is a lead forerunner. Now, what's all this fuss about nanowires anyway? Well, as the name implies, nanowires are one-dimensional structures with really high aspect ratios. In fact, the diameters are typically on the order of 10 to 100 nanometers, hence the word nano, and the lengths are typically on the order of 10 or greater micrometers. And it's found from past work that as we scale things down to the nanowire level, we really positively influence all of these categories. And that makes sense. I mean, the smaller something is, the less energy it'll take to switch or do whatever it has to do. And this is part of a larger research area into size-dependent properties. But we don't want to digress too much. So what we need to know is that today, nanowires are fabricated using what's called the vapor-liquid-solid mechanism. And VLS is great because we get a lot of nanowires, as you can see. But the difficulty arises when we want to orient these nanowires into a device configuration that maybe looks something like that. So people have tried doing this all over the world and to little success. So what they usually do is make a single-bit device like that, test it, call it proof of concept, and move on. It would be really nice if we could come up with a bottom-up approach to pre-orient these nanowires so that we don't have to go through this difficult manipulation process. Enter my proposed vapor-based step-edge decoration. This draws inspiration from past work on electrochemical step-edge decoration, which takes place in solution. In my method, however, we start off with a quartz tube with an inert argon flow. We then put our precursor in the middle of this tube, in this case germanium telluride, phase change material. When we heat it, it forms a vapor which is carried to the downstream end. There it sees what's called a highly oriented pyrolytic graphite substrate. Now that's a mouthful, but what that means is at the atomic level, it has these little step edges. And when incident upon with the vapor, these steps act as little nucleation sites for the GET to precipitate out. And over time, we form more nuclei until they coalesce and form continuous nanowires. And these happen to have the property that they're parallel. Now, I know I've hyped these wires up, so let's take a look at what they actually look like. There we go. Parallel-oriented nanowires of uniform diameter. Pretty cool, especially when we compare them to what we had before with VLS. So now that we have these nanowires, we need to find a way to transfer them from this substrate to an electrically insulating substrate so we can actually make devices on them. Unfortunately, that's where past work was of little help. In fact, this was a turning back point for a lot of groups working on electrochemical step-edge decoration because they just weren't able to get the wires off the substrate. So I tried all of these methods, which were documented in literature, and unsurprisingly, they all failed. So I had to come up with my own optimized technique, and I'll run that by you here. So we start off with our HOPG substrate, which has nanowires on them. We then form a PDMS film right on the substrate. PDMS is a highly cross-linked polymer. It's just, you can think of it as something very sticky. So we form this film, and once it's cured, we can peel it off, and the wires remain embedded in the film. We can then place that film on our insulating substrate, let's say SiO2. And then here's the key step. We treat it with oxygen plasma. And this oxygen plasma breaks the bonds of these cross-linked polymers, allowing us to remove the polymer, leaving behind the wires. And this really works. So, to appeal to my single-bit brethren, I made a single preliminary electrical device and ran an IV sweep on them. And what do we see? Perfectly, almost linear IV curve. This is really encouraging because it means that we don't have any carbon or contaminants shorting the system. And we are even more hopeful because the resistance that we measure is right in line with the resistance for these phase change materials. So that works. Now, fueled by my success with the transfer process and the fabrication process, I wanted to see what I could do with this technique. A logical new next material to try was germanium, And after optimizing the growth conditions there, we now have parallel-oriented germanium nanowires too. What about next generation photonic and plasmonic applications? Well, we have preliminary data showing cadmium selenide can be fabricated using this method as well. This requires a little bit more optimization. I started this about 2 weeks ago, so, but we do have data that this works. What about our generation's most favorite material, silicon? No problem, we can do that too. And for those of you who want to throw back to good old metallurgical times, we have titanium as well. So, what I can say here is that we're really rekindling step edge decoration, and SED is here to stay. It's really discouraging when people like Reginald Penner come out with statements claiming that, the step edge decoration is a nuisance. Well, I believe it's a nuisance only in electrochemical form. I think my vapor-based technique has some really cool advantages. For one, it's just easier to use. There's a reason why industry uses vapor-based techniques. They're easy to implement, and and my method is very easily adaptable to a lot of different experimental setups. Next, we have a lot of growth parameters in vapor-based techniques. This allows us to tune the pressure, mass flow, temperature, etc., to influence the outcome of what wires we get. In fact, I've been able to very precisely control the diameters of my nanowires. As you can see here, the standard deviation after 60 minutes is about 6 nanometers, which is right in line with about cutting-edge bottom-up technology today. So this process is really, really pushing the limits. The next reason why I think SED is here to stay is because we actually have a transfer method that works now. In the past, groups had to make their devices on their adhesive itself. I can completely remove the polymer adhesive, leaving behind pristine nanowires. And finally, I've shown applicability to a variety of material systems, implying that they could in fact be used with other material systems that I haven't yet tested. So what am I saying? I'm saying I'm changing the game. In the past, in order to create oriented nanostructures, we had to use really expensive lithography techniques in clean rooms like you see here. And this is a really expensive process. We were then motivated by bottom-up techniques which were versatile and easy to do, but required a lot of time and effort to manipulate these wires into a device configuration. My method bridges the gap. It combines the parallel patterning ability of lithography with the ease and versatility of bottom-up techniques. So with that, I want to look to the future. And when I look to the future, I'm saying that the future is almost here. And that's not to sound metaphysical in any way. I'm saying it actually is very near term with this technique. One of the leading research fields today is in flexible electronics. And one of the biggest problems they're having is when they scale down the electrodes, they're having trouble retaining the orientation of the electrodes. This isn't a problem for us because if you actually remember our transfer process, what we're doing is embedding these nanowires in a polymer film, and I've shown that these retain their orientation. So with a little bit of optimization and tweaking, this should be a very near-term solution. After that, as per the motivation of this talk, for the electrical engineers in the room, given a parallel bit structure like this, it's not unforeseeable to form a crossbar architecture and form a memory device. That we can talk about that if you're interested. And then after that, if you really want to push the limits of nanotechnology, past work in our group has shown that we can create all optical switching for gates, and we actually created NAND and NOR gates using only nanowires and light. And because I knew the guy who made these devices, I know what took him the longest time was hoping that his random growth process would yield 2 wires that were oriented like this. Now we can take the guesswork out of this and move one step closer toward forming multi-bit light-based computing devices. I have no doubt that the next big innovation is going to come from something small, like a nanowire, and I hope that my method is going to bring us one step closer to that. As you can tell, I'm very excited to have worked on this project, and it has tremendous application in the near term as well as in the far term. But I wouldn't have been able to do this without the support of the Agarwal group in the back, as well as the MSc department and the overall SEES community for their support. Thank you very much, and I would love to entertain any questions.
How did you get the idea for your transfer mechanism?
That's a good question. It actually follows from some of the unsuccessful techniques that I tried. A common method of transfer is to use PDMS actually as a stamp. So they sort of stamp it on and then stamp it on something else. I tried that, but that's pretty much the same as like a Scotch tape method, which clearly wasn't working. So I actually said, one day instead of stamping it on, why don't I just make the film on there? And thanks to actually a polymers class that I took, I knew about how PDMS cures, and it's the fact that it's very cross-linked. And I thought maybe if that can't get these wires off, I don't know what can. So that was the motivation. It was more just I was pretty frustrated with nothing working, so I gave it a shot. Questions? I did that good of a job.
For a memory device, is there any power needed to keep the stable bits?
Yeah. So the nice thing about phase change memory in specific is that it's a non-volatile memory device, and that means that, like your hard drive, when you turn off the computer, turn off the power to the computer, you can actually retain information. And that's one of the criteria for a universal memory device, and that's why we're so excited about this material. So you do not need power to retain the information. Yeah. That's a good call. The next step in terms of research is to actually make one of these functioning devices. In terms of a near term, we are actually in talks with, we're going to reach out to CTT to try and, to see what we can do, whether we should go the academia journal route or the patent route. I'm leaning towards the journal publication, but we'll see. Fingers crossed. I don't want to